A single retried webhook delivery can trigger multiple database inserts, creating phantom inventory or duplicate ledger entries in your enterprise resource planning system. Network timeouts often lead clients to retry requests that the server has already processed, resulting in inconsistent states across your distributed IT architecture. Idempotency ensures that performing an operation multiple times produces the same result as performing it once, which is vital for maintaining financial data integrity. The core solution involves an idempotency-key, a unique identifier sent by the client that allows the server to recognize subsequent retries of the same request. Clients should generate a universally unique identifier version 7 for each new operation, ensuring the key is persisted before the first transmission attempt is made. Use the standardized X-Idempotency-Key header in your API requests to maintain consistency across different modules of your enterprise resource planning suite. Upon receiving a request, the server must immediately check an internal idempotency table to determine if the specific key has been processed or is currently active. Your idempotency table requires columns for the unique key, the request hash, the current processing status, and the serialized response body for completed operations. Execute an atomic insert or a select for update statement to claim the key, preventing two concurrent requests from processing the same webhook simultaneously. If a lookup reveals a status of started, the server should return a 429 too many requests status code to indicate processing is ongoing. Store a hash of the request body alongside the key to detect if a client reuses a key for a different operation, which should trigger a validation error. Once the key is locked, proceed to execute the business logic, such as updating inventory levels or creating a sales order within the primary database transaction. Ensure that the business data update and the idempotency status update are committed within the same database transaction to prevent partial state failures. After successful processing, store the final hypertext transfer protocol response code and body in the idempotency table before releasing the lock and responding to the client. When a retry arrives for a completed key, retrieve the stored response from the database and return it immediately without re-executing any business logic. While the transactional outbox pattern ensures message delivery, the idempotent consumer pattern is what guarantees that the receiving end handles those messages safely. If the idempotency database is unavailable, you must decide between failing open to maintain availability or failing closed to ensure absolute data consistency. In high-volume microservices, use a fast key value store like Redis to manage transient locks before persisting the final state to a relational database. Implement a time-to-live strategy for your idempotency records, typically retaining keys for 24 to 48 hours to balance storage and safety. Set up an automated background job to delete expired idempotency keys, preventing the table from growing indefinitely and slowing down your primary lookup queries. Prefer time-ordered universally unique identifiers for your keys to maintain high database insertion performance while providing enough randomness to prevent collisions. While collisions are rare with 128-bit identifiers, appending a tenant identifier to the key scope provides an extra layer of safety. Implementing idempotency as a middleware component allows you to decouple your core business logic from the mechanics of request deduplication and response caching.
Operations involving third-party application programming interfaces, such as sending emails or processing payments, require careful coordination within your idempotent flow. If an external call cannot be rolled back, execute it only after successfully locking the idempotency key, but before marking the status as completed. Log every time a duplicate key is detected to gain visibility into network instability or client implementation issues within your system ecosystem. The overhead of checking the idempotency store is minimal compared to the cost of recovering from duplicate transactions in an enterprise resource planning environment. For massive global scale, consider partitioning your idempotency table by key prefix or tenant identifier to distribute the input and output load. Protect your idempotency endpoint from denial of service attacks by implementing rate limiting alongside the key validation to prevent database exhaustion. Clients should use exponential backoff with jitter when retrying failed requests to avoid overwhelming the server during periods of high congestion or recovery. When processing webhooks from a message queue,
Ensure the consumer uses the original webhook identifier as the idempotency key for all downstream system updates. Test your implementation by firing identical requests simultaneously from multiple threads to ensure your locking mechanism correctly handles extreme race conditions. Use chaos engineering tools to drop acknowledgement packets, forcing your client to retry and verifying that the server never duplicates the business action. Many modern frameworks offer built-in support or plugins for idempotency, which should be prioritized over custom implementations to benefit from community security audits. If you must integrate with a legacy system that does not support idempotency, build a proxy layer that manages keys and ensures single delivery downstream. Maintaining an immutable log of processed idempotency keys serves as a critical audit trail for financial regulators and internal troubleshooting teams. Returning a 200 OK status code for duplicate requests is common, though some developers prefer 209 to explicitly signal a duplicate. The hypertext transfer protocol delete method is naturally idempotent, as deleting a resource that is already gone should typically result in a success code. The put method is intended to be idempotent by replacing the entire resource state, unlike the post method, which usually creates a new resource.
Successful idempotency requires 4 steps: receive the key, check for existence, execute logic atomically, and store the result for future identical requests. When handling massive payloads in your webhooks, only store the hash and metadata to avoid bloating your idempotency database with redundant large data blocks. In a multi-node environment, ensure your persistence layer provides strong consistency rather than eventual consistency to prevent windows of vulnerability during key checks. Start by implementing idempotency on financial endpoints first, then expand to inventory and master data management as your enterprise resource planning integration grows. When a key collision or validation error occurs, return a structured JavaScript object notation error response that clearly explains the conflict to the calling system. Create a unique index on the idempotency key and the tenant identifier combination to ensure the database can perform lookups with sub-millisecond latency. Before going live, verify that your idempotency table has proper indexes, an automated cleanup job, and that your logic handles the started status correctly. Implementing idempotency is not just a technical task, but a strategic investment in the reliability and trustworthiness of your entire enterprise resource planning data ecosystem. By implementing rigorous key validation, atomic database persistence, and automated cleanup routines, you ensure that your enterprise resource planning system remains a single source of truth, even when facing the inevitable chaos of distributed network environments and unpredictable webhook delivery retries.